Again, so now we're going to pick up where we left off on our introduction to momentum. And we're going to basically develop a new way of looking at the second law of motion. And it's a more general version. In fact, it's the way Newton originally wrote it when he published Principia back in the late 17th century. Okay, so it's building off the idea of the Biff problem above. So let's get right to it. This is a very simple derivation. The equation that comes out of it, really important. And then the good news is we don't have to apply it for a lot of situations because, you know, most of the time kids don't like new things because it just makes things more complicated for them. So let's look at the second law of motion again. A net force we know is equivalent to the product of a mass times an acceleration. Okay? Now, there is a basic assumption about this form. And I mentioned this way back when I introduced the second law. We haven't talked about it since because it hasn't come up, but now it is. Now it is coming up. And that assumes, this equation assumes that mass remains constant during the interaction. In other words, when you exert a force on a cart or a ball or a person, the mass of the person or the object in question isn't changing. And that's usually the case, okay? But in something like a rocket, where as it is ejected, whereas as the rocket's fired, it's ejecting material at a very high rate. So the force that you get from that can be makes it move, but to apply the second law it becomes more complicated because your mass is changing. So we need it, like I said, in more general form. So let's take the F equals ma and let's break it down. Well, by definition, a is the rate of change of velocity. So we can rewrite the second law of motion as F equals m delta v over t. Okay? Now, I want you to look at that numerator real carefully. M times delta v. Well, if you ignore the delta, that's m times v. And hopefully you know now, m times v is momentum. And so with the delta in there, that just becomes delta p. So the second law of motion can be written as force is delta p over t, the rate of change in momentum. And that's the most important and general form of the second law of motion. Mass is the rate of change of momentum. So that can be written as two ways, and I'm going to do it right here, and we'll see where the second way, which you haven't seen before, becomes relevant. So again, delta p is the change in momentum. Well, there's two ways you can change momentum. Actually, there's three ways, but we're just going to do two. That could be the mass stays constant and the velocity changes with time. That's the traditional ma. Or it could be the mass changes in time, that's a rocket, at a certain velocity. So that's another way you can write delta p over t. These two are different versions of the same thing. And in fact, in most general, and we're not going to have to worry about that, you could have both changing at the same time, and that's more complicated. That requires calculus to have to solve that. So now what we do is when the mass of the object is changing at a constant rate. In other words, a rocket. So let's finish up with a problem like that. So let's say at the moment of takeoff, a rocket expels propelling gases at a rate of 1,200 kilograms per second. Look at those units, because we haven't seen that before. And it does so at a speed of 50,000 miles per second. So the gas is leaving the rocket at a very high speed. And so what's the point of that? Because we want to propel the rocket using the third law of motion. So to understand what force is exerted on a rocket, we got to understand what force is exerted on the expelled gas, which we're going to use the rate of change of momentum. And this is why it's a more powerful idea. So first of all, we got to understand this 1,200 kilograms per second. Well, if you look at the units, kilograms is mass, seconds is time. So this is the rate at which mass is flowing out. So it's called mass flow rate. So that's a new term for us. So the symbol for mass flow rate I'm going to use is an m dot. Okay, this is from calculus, but it's not hard to understand. Mass flow rate, by definition, is the rate of change of mass over time. Okay, where, if you will, x dot would be, by definition, delta x over t, and that's velocity. Okay, v dot is by definition delta v over t, which is acceleration. So the dot indicates the rate with respect to time. And of course the 50,000 meters per second tells us that's the velocity of the gases. Now let's apply the second law of motion for a more general form. We have then the force, that's what we're trying to find, F equals the rate of change in momentum of the gas, which in this case is going to be delta M over T, the mass flow rate, times the speed. So I don't need the amount of time. It's built into this whole thing. So in other words, that delta M over T is just M dot V. No, so that's the 1,200 kilograms per second times the 50,000 meters per second. And we get a really large number, a really large force, 6 times 10 to the 7th newtons. And this would be kilograms per second times meters per second, which would be, you can work it out, kilogram meters per second squared. That's why it's a newton. So we designed rockets to give us that much force to lift that heavy rocket, and more importantly, to give it enough speed so we can either put it in orbit or have it escape the Earth altogether. Okay, so try this. Let's apply it to a hose. In a hose, you're ejecting water. So in this case, we have a hose with a speed of 20 meters per second, and it's leaving at a rate of 1.8 kilograms per second. That's the flow rate. That depends on how big your hose is. If you have a fireman's hose, you're going to get a bigger flow rate than a small garden hose, even though the speeds could be the same. It hits the side of a car and comes back, or comes to a stop. No, there's no splashback. That would just complicate things a little bit. What force does the car impart on the stream of water? Okay, so the idea on this is the car hits the water and makes it stop. So the force on the water due to the car is the rate of change of momentum of the water. Okay, now since the water is flowing, the amount of mass coming out of the hose is continuously changing. So we can't just do M times A. What we can do is just translate that to M dot, times V. Okay, and that's again the same thing we did with the rocket above. So M dot is right there, kilograms per second. Again, that's the flow rate, times this hose is coming out pretty fast. And that has to do with maybe the diameter of the hose, etc. And anyway, we multiply that, we get 30 newtons. So if that's the force that the car exerts on the water, you usually care about what does the water do on a car. In other words, it's going to blast things off like a pressure, high pressure hose. And the answer is also 30 newtons because of the third law of motion. And then we could ask how much water was used in 30 seconds. So how much water is the mass? What mass of water came out of the hose? Well, we know that M dot is by definition the rate of change of mass. So the change in mass, that's what we want, is the same as M, how much came out, is simply equal to the rate that it comes out multiplied by time. So our rate is 1.5 kilograms per second again. For 30 seconds, that means there was 45 kilograms of water. Okay? So sometimes kids get confused between this and this. And I want you to understand, when I define delta M over T, it's just one quantity. We don't necessarily have to separate the time if we don't need to. So that concludes the first part of our introduction to momentum. The next topic, which will be a separate tutorial, we'll look at something called impulse, which is a variation of what we just talked about.